Okay. Hi, everyone. I am Ms. Marrero. I am going to be working today on optimization. So in class, we have been talking about minimums and maximums and how to find these. We use the first derivative test. We use the second derivative test. We graphed to check our answers, right? So now we're going to go ahead and actually use those in something, in context, a real life exercise. Okay, so this section is called optimization. Our learning objectives are to calculate the minimum and maximum values in applied context over an interval and interpret the minimum and maximum values calculated in applied context of functions. Okay, so this is the packet that you have right now. I am going to be working, you know that I like working on Paint. I like to, so I would like you to take a minute to first read the exercise. I decided to start with this exercise because it's something that you most likely have seen or at least have worked a little bit with. So take a minute and read, pause this video and go ahead and read. Okay, so I'm gonna read it out loud. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions should the box be in order to produce a box with a maximum volume? So we are talking about a box and we have some information given, right? So what do we know about this box? Well, I am going to underline the information that we have about the box. Okay, so let's see. It has a square base, meaning that's both sides, the same, they have the same length, right? It has a surface area of 108. Do you remember what surface area means? If you don't, go ahead and Google it, right? But surface area is nothing else than the sum of the areas of all the sides of the box. Now, there is a very, very important thing that we need to watch for here. Let's see if I can, no, I'll just make this a little bit wider. Okay, and there's this thing. It is an open box. So what does that mean? Well, it means that one of these sides, the square box, right? This drawing is kind of misleading, right? Okay, so I'm just going to go ahead and change this to H and this to X, right? So that we have one of these sides, one of the bases, okay, is not there. So when we consider the surface area, we do not consider one of the bases, okay? What dimensions should the box be in order to produce a box with a maximum volume? So ultimately, what we want to find is the dimensions for a maximum volume, okay? So let's see, what do we know about volume? What is volume? You know that volume is whatever fits inside, right? It's the amount that fits inside. To find the volume of a box, it is going to be length times width times height, right? So this is easy, right? Okay, so we have the length and the width are X. Ooh, but we don't know H, right? So we have that V then, the volume equals X squared times H. So this seems a little bit like, we need to figure out something, right? We don't know really much about the volume. We don't know much about X or H. So we need to use the other piece of information that we have, and that is surface area, right? So surface area is the sum of the areas of both the sides, okay? So go ahead, pause it, okay? Pause this video and look for the surface area, please. So now that we're back, so we know that we have 4 sides with area XH. So this is going to be 4 times XH plus Oh, but remember, we don't have one of the sides, so it's the area of only one of them, x squared, right? But we also know that the surface area is 108, right? So this is 108, right? So let's see, let's put this information here. We have volume equals x squared times h, and we have that x squared plus 4xh equals 108. We have two equations, two unknowns. This is basically a system of equations, right? So let's go ahead, since we want to find the maximum, the dimensions for the maximum volume, right? So we want to work this. So this is going to be our primary equation, and later we'll discuss this, right? But this is what I want to get to, right? I want to work with this to get my answer, get my maximum, the dimensions yielding the maximum volume, right? So I'm gonna work with this one, okay? Notice that we can leave the h by itself. So h is going to be 108 minus x squared, everything over 4x, right? And then I can put it in my primary equation, which is x squared times h, which is 108 minus x squared over 4x, right? Now I'm going to go ahead and I'm going to just multiply this x squared, and this is 104 divided by 108 divided by 4 is 27, and then this is going to be x minus x cubed over 4, right? So this is my volume, right? Okay, so before we continue, let's talk about possible values of x, right? That would be the domain, okay? The domain. So obviously the x cannot be negative, right? Because we're talking about sides. Can it be 0? If it's 0, it's not a box, right? So we have some information here. X has to be greater than 0. If not, there's no box, right? Also, well, we also wrote the well, it just cannot be 0, right? And we know that the denominator cannot be 0. Now we also need to make sure that this up here, right, in the numerator, right, the height cannot be 0 either, right? So let's do this in a little corner here. 108 minus x squared equals 0. So I solve this, and then x equals plus or minus square root of 108, right? Okay, we cannot work with the negatives, right? So the largest possible value for the x is going to be square root of 108. And we're not going to include it, because if we did, then the height would be 0 and there's no box, right? So the domain, then it's going to be between 0 and a square root of 108. This is important because if this endpoints were included, we would have needed to use eventually the candidate test. Remember that when we have a function, right, in a closed interval, there is a guaranteed absolute maximum and absolute minimum, right? In this case, there's not, okay? So going back to our exercise, okay, I'm gonna kind of divide this here, okay? And now when we talk about maximums, what do we think about, right? We're in calculus, we think about, hopefully you said critical points, right? Critical points. And that's where the derivative, right, equals 0 or is undefined, right? And then we check to verify that one of these is a minimum or a maximum or neither, right? Okay, so let's see. V prime is, well, the derivative of this is 27 minus 3x squared to the over 4, okay? So this is never going to be undefined, never undefined, okay? So we just write there, okay? So this is going to be equal to 0, right? So we check where it is equal to 0. So we have 3/4 x squared equals 27. From this, we get x squared equals 36. We do the square root on both sides, and we get that x equals plus or minus 6. But because we are talking about sides, we do not use the negative, okay? So now we have part of the information, right? Okay. Well, we would like to say, oh, so x is 6, right? 6, 6, and then we can find h, right? But we first need to make sure that this is a maximum, okay? And we can decide to do the first derivative test or the second derivative test. I am going to do the first derivative test, okay? But remember, we should always practice both, okay? And I'm going to use my number line. So this is 6, here it's 0, right? This is v prime. So when it is, say, 10, right? This is going to be a large number. This is negative. When it is, say, 1, okay, this is going to be a smaller number. I'm talking about this here. So this is positive, right? So the derivative goes from positive to negative, meaning it goes from increasing to decreasing, right? So we know that there's a maximum, okay? So v has a maximum, a relative maximum at x equals 6 because v prime changes from positive to negative, okay, by the first derivative test. So yes, we have the maximum, right? So we have the x. Now we need to find the other dimensions, right? Also, this is 6. This is 6, right? Okay, so now we need to figure out how much is h, right? Well, we found that h is this, right? I'm working here, right? So I'm going to plug in the 6. So then h equals 108 minus 6 squared, which is 36, divided by 24. That's 4 times 6. So this is 72 divided by 24, and this is 3, right? So now let's go ahead and let's answer our question. What dimensions should the box be in order to produce a box with a maximum volume? Well, the dimensions are the dimensions for a maximum volume would be 3 inches, right? Are we talking about inches? Yes. By 3 inches. Oops, no, sorry. 6 inches by 6 inches by 3 inches. Okay, let me fix this a little bit. I don't like that. Okay, so yeah, 6 by 6 by 3. Okay, so, okay. So how am I going to write the answer? So I'll write 6 by 6 by 3. Okay. Okay, very good. Okay, so now let's go ahead. So hopefully you don't have any questions. If you do, remember, you can always ask me in class. You can email me at any time. Okay, but let's review what we did. Okay, we started with some information about an open box. Okay, I'm not gonna lie, the open box is a little bit tricky because we think of the box, right? It has 6 sides, right? So that we have to be very careful with. It has a square base, okay? So that's information that is giving us, you know, that 2 of the sides are gonna be the same, and it has a surface area, right? Then we were talking about volume, okay? Ultimately, we wanted to find information related to its maximum volume. So we made the equation of the volume the primary equation, and the other equation that we had to work with, it wasn't really what we were looking for, but we were gonna use to get there, was the surface area, okay? So what we did, we created a primary equation, the one that I wanna find, okay, the ultimate one. a secondary equation, which is the one that gives me the information that I have right now to work with. And then we worked a system of equations to relate both of these, and then go to the optimization part, which is our calculus portion. In this case, we wanted to find what the dimensions for the maximum volume. So we were looking for a maximum in this case. And going back into our calculus course, right, we find first the critical points, which is where the derivative is 0 or undefined. In this case, there was no point, no x, where the derivative was undefined. So we just worked with the derivative equals 0, right? Okay, very good. Then we found that the derivative equals 0, the critical point, happens at x equals 6, right? And then we figured out using the first derivative test whether this was a maximum or a minimum. Okay, I kind of left there that we check the domain of the original function, right, of the volume. Okay, because remember, so we had to check, because if we do include the endpoints, remember it works a little bit different, right? But in this case we don't. Okay, so we didn't have to worry about the endpoints, because at the endpoints there would be no box. Okay, so we found that the maximum volume occurred when the square base was 6 by 6, right? And this happened because the derivative changed from positive to negative. We plugged in the h and we found h, okay? The height, which is the height, right? Okay, so the dimensions that yield the maximum volume then are going to be 6 by 6 by 3 inches, okay? I have all these instructions here for you. Let me see, where's my cursor? Okay, here it is. Oh, here it is. Okay. Okay. So this, I guess I forgot about this. Okay. This was just showing, you know, there is a few boxes that have a surface area of 108 square inches, right? We just needed to find the one that yields that maximum volume, right? And that's what we did. Okay. So these are the guidelines to solving applied minimum and maximum problems, right? First, identify all the given information and what needs to be determined, okay? If helpful, make a sketch. Do you know that I love sketches, okay? For me, you know, that's a must, sorry. Write a primary equation for the quantity that is going to be optimized, right? So in this case, we work with volume, right? The primary was volume because this is what we wanted to maximize. In our case, it could also be minimized. And then reduce the primary equation to one having a single independent variable. And this may require the use of the secondary equation that we create, okay? Determine a feasible domain for your primary equation. Okay, so obviously, you know, when we talk about volume, we talk about positive quantities, not 0, because if not, there's no figure to find the volume of, right? And then determine the desired maximum or minimum value by using the techniques that we have learned before, okay? This includes taking the derivative and finding critical points and setting up a chart if necessary. Okay, so I hope you understood this. Again, okay, I'll see you in class. I'm always here to answer any questions. Okay, so thank you. Bye.